Hi, so I'm going to be working through problem 15.P.71. This problem I've redrawn for you. It involves a spherical plastic shell with a uniformly distributed negative charge, and then it is next to four charges that are packed really close together. These charges are also pictured here. So basically, they're a distance L apart, which is significantly greater than a distance S of each dipole with the four charges. So part A asks us to calculate the x and y components of the electric field at location B, which is pictured a distance little b to the right of that plastic shell. So what we're going to do is we're going to look at first the field created by the plastic sphere by itself. So first, let's look at that. If you just go to our formula sheet, we're actually going to treat this plastic shell as more of a point and use that formula. So we get formula 1 over 4 pi epsilon naught with a negative q on top. And for our radius value, we're going to do a distance r, which is the radius of the circle, and adding to that value of little b, which is the distance immediately outside the circle. So to put that into vector form, if you look to the right, you're actually going to put a negative value. It's going to be in the negative x direction because it is a negative charge, and the y and z values are going to be 0. The second electric field that we need to take into account is from the first dipole, which are going to be those two charges that go up and down in the y direction. So again, from our formula sheet, we will look at the electric field of a dipole, use that formula, and for the radius, again, we're going to have to use L this time, plus a radius R, plus a little b in that section of the formula. And putting that into vector form as well, as we see from that drawing on the left with the dipole face in that direction, that E field is expected to be in the negative y direction. So we get a 0, a negative y value, and then a 0 for that vector. For the second dipole, this is going to be the one laying in the x plane. We're going to use again an E field formula from the formula sheet, this one for the parallel on axis dipole formula. So it's just going to add a 2 up to the top of our formula, again using the exact same amount for the radius as with the dipole before. Again, looking at the drawing, you can see that this E field is going to actually be in the positive x direction. So to get our final E net, we're going to add up these three that we've already calculated, the electric field due to the negative q charge on that sphere, the E parallel dipole, and the perpendicular dipole, and you can see those values in vector form on the screen. Part B asks for what simplifying assumptions did we make for Part A, and that was something they already told us, that L is significantly greater than a distance S, which allows us to use those E dipole formulas. So in Part C, they kind of changed the game a little bit. Instead of having a thin plastic shell, they've replaced it with a neutral metal ball. So now they want to ask us from a location A, which is actually inside the ball, a distance, again, little b inside the ball, what the electric field due to the ball is, and then what the electric field due to those 4 point charges is. So first we're going to look at the E field at point A given by the 4 charges, and that was actually given in part A, at least the direction, the general direction, in the vector that we found at the end, which was in the positive x, negative y, so that's just a rough sketch drawn on there. So how do we find the electric field given by the ball itself? So we know that the E field net inside of a conducting material has to be zero. So the two components that we're concerned with is the E field created by the four charges, but also the E field created by the ball, which is what we're looking for. So if you kind of set up that equation and solve it, we know that the E field of the ball is actually just going to be the E field caused by those four charges, negative. So we can have that pointing the exact opposite direction, coming from point A. Part D asks us to show the distribution of the ball surface charges. So in order to do that, we basically just look at the E field created by the ball, which we just found, and in order to make an E field in that direction, you have to place the surface charges in this particular formation, with our electron C moving to that bottom right corner, and the positive charges being collected at that top left corner, and that will give you that particular E field. So part E asks us to calculate the x and y components of the electric field at location A. So in order to do that, we will set up our equation again. We know that the E net inside a conducting material has to be zero. Our E net in particular is composed of the electric field created by dipole 1, the electric field created by dipole 2, and then the electric field of those surface charges. So we're going to solve for the surface charges to get that electric field at point A, which is just going to be negative of the electric field from dipole 1 adding to the electric field of dipole 2. So plugging in the values that we get from our formula sheet again, for dipole that is perpendicular, we use just the QS on top, and for the radius, we're going to use the value of L plus little b, which is the location inside the sphere of point A, and then the same thing for the X component, except for this is the dipole, which is parallel on axis, so it's going to be 2qs on the top, same value for r, and then when you distribute the negative through, and I pulled out the 1/4 pi epsilon naught, and these are your x and y components.